Welcome again to a new video of Da Vinci Design and Engineering. And today I want to discuss with you the Fourier Series. And the Fourier Series is a very important phenomenon to represent a signal as a summation of cosinuses and sinuses, and that's very important to know how to do this, because we will see that the applications, there are a lot of applications for it. So let's start. Like I said here, the idea of the Fourier series is to represent a signal as a sum of cosinuses and sinuses. And what I mean by this is, suppose we have this summation, or this representation, I have to say, of cosine omega t plus b1 sine omega t plus a2 cosine 2 omega t plus b2 sine 2 omega t, etc. And where the omega is the forcing frequency in radians per second, of course. And I can write equation number 1 shorter, like this. Xt is a naught plus the summation from n is 1 to infinity of an cosine n omega t plus a summation from n is 1 to infinity of bn times sinus n omega t. So you can see that this equation here is now has been written in a more shorthand form with infinitely many terms. These terms, and more in general, these terms are called the Fourier coefficients, or Fourier expansion coefficients. Let's just write an and bn are coefficients. So if we know those coefficients, we know how to represent a signal. For example, this signal or function. We know how to represent it with a summation of cosine functions and sine functions, like we wrote here in equation 2. So xt is then an approximation or representation of, for example, this function it, for example. One important thing to know is that the Fourier series are only valid for periodic functions. That's the limitation. So the Fourier series fs are only valid for periodic functions. So this is this pattern. For example, if this is 1, this 2, 3, 4, this is a kind of a block function. It's repeated for all time to infinity. So like I said earlier, the goal is to find those coefficients a naught, an, and bn, and how to do this. So goal, find the coefficients a naught, an, and bn. If we look closely to this expression here, to equation 2, since cosine and sine functions are periodic and they are oscillating around 0, you can see that a naught, it determines the shift from the x-axis or the time axis. So a naught is the average value. A naught is the average value. And how can we write an average value in a more mathematical sense? Now, by doing this, a naught is 1 over t integrated from over one period of the function xt dt. This is an average value because we compute the area inside one period below the curve of x of function of t, and we divide it over the length. So in essence we have an area divided over the length, and that's the average height, so the average value. So this one is quite easy. And we can write it, we can derive this expression also in a more formal way. Let's do that. We then have, if we go back to equation number 1 or 2, it doesn't matter. What do we have then? We have this. We integrate each term of equation 1 over one period t naught. And we do that also with the right hand side of the equation. So this is the left hand side and this is the right hand side. And if we do that, we obtain this plus t naught times a1 cosine omega t dt plus integral t naught b1 sine omega t dt, etc. plus all the terms, all the n terms. And if we integrate a periodic function over one period, it's just 0. So all those terms become 0 except of this one. So what do we have then? We then have the integral of xt over one period is equal to a naught times t naught. So a naught is 1 over t naught times the integral of t naught of xt dt. So this is our first coefficient. We proved it now in a more mathematical correct sense. Okay, let's go to the next item. And the next coefficient to prove or to derive is an, coefficient an. So if we pre-multiply or post-multiply now every term of equation 1, this equation, with cosine omega t. So if we consider a1, then we multiply equation number 1 with cosine omega t. And if we want to determine a3, then we do the same, but then with cosine 3 omega t. And in more general, an, we multiply equation 1 with cosine n omega t. And you can see those cosine n omega t as a kind of a weight function. Weight function. So let's do that. So what we then obtain is this, the integral of xt times cosine m omega t dt is equal to the integral of a naught times cosine m omega t, or n omega t, it doesn't matter, plus the integral of t naught of all the other terms. And let me write it like this. Cosine m omega t dt sorry, I'm make no mistake. It's like this, of course. Yeah. And this is of course n, because this is the coefficient and this is m. Yeah, now it's right, plus the last integral. Bn times sine n omega t times cosine m omega t. So here you can see that we take the infinite sum of all these separate coefficients. And since we already saw that an integration of over cosine is 0, this term already cancels. And now we have only two terms left. This term related to cosine terms and this one related to sine terms. And to see how we can proceed, we have to use orthogonal properties. And what is that? Now, for example, if we have our first property is that the integral over a period of sine m omega t times sine n omega t dt is 0 if m is unequal to n, and it's t over 2 if m is equal to n. The second property is the integral of cosine m omega t times cosine n omega t dt is 0 if m is unequal to n, and t over 2 if m is equal to n. And I forgot one thing, important remark. M and n are integers. That's very important to know. In literature you can often m and n are called the mode numbers. Mode numbers. Or the number of the node. Of the mode, sorry, modes. Okay. And the third property is that the integral of sine m omega t times the cosine of n omega t dt is always 0. So if we take into account those properties, we can directly see, since this is 0 for every term of n and n, this term cancels out and we are only left over with this term, which I will again write for you. We then obtain the integral of t naught times xt cosine m omega t dt is the summation of an integral t naught cosine n omega t cosine m omega t dt, and we can now see that we then will keep that the integral of t naught xt cosine m omega t dt is equal to an times t over 2. Because the only, this will never give an output, it's always 0, except for the case that m is equal to m. So the summation from 1 to infinity is just t over 2, and before we had here a coefficient which I replaced here. So that's the reason. So we are almost there. So then we know that an is equal to 2 over t times the integral of xt cosine n omega t dt. So here we had the formula for first coefficient, and here is the formula for our last coefficient. And if we do this computation again, we then obtain for Bn almost the same, but slightly different. It's just this. And please derive this by yourself at home. But the idea and explanations are exactly the same. Okay, that's it for today. Thanks for watching. Don't forget to subscribe to the YouTube channel. Next time I will use these formulas which we derived for an example. So then it becomes even more clear for you. So again, thanks for watching and see you next time.